Hi everyone, today we're going to be talking about the Z-score, or the Z-score as we pronounce it in the UK. We're going to say what it is and what we can use it for. First of all, let's state what it is. Now, say we've got a random variable, say x. It is distributed normally with mean mu and variance sigma square. Well, what does that mean? It means we've got a whole list of numbers that if we sketch a histogram, it's going to be a bell-shaped curve. This horizontal axis are the scores. You should taper away towards 0 if we go far enough. Okay. And what we can say is that the center, this particular value, which coincides with the peak of this, will be the population mean of x, and kind of the spread of this thing is measured by the standard deviation or the variance sigma squared. Now the z-score takes us from the x random variable to the z random variable, which is also normally distributed, but it's got mean of 0 and a variance of 1. So how this looks on a histogram, z on the horizontal axis, bell-shaped curve again. Not great at drawing. And this time it's centered around 0 with the variance of 1. So what's the equation that actually links the x to z? That is called the z-score. The equation is z equals, take the x value, which is just a number, loads and loads of different numbers, subtract from it the mean of this x, which is here. That will be a number. We're just using the symbol mu to denote that number, and divide it by the standard deviation. Now this slot always contains the number for the variance, so we want the square root of that. Since this is just a symbol to denote the variance, we just need to square root that, so the symbol for the standard deviation is sigma. So to recap, x will be a value, the score. Mu is the mean of x. Sigma is the standard deviation. Note it's not the variance, it's the standard deviation of x. And this equation says that if we take our value x in our original data, subtract it from it the mu, divide by sigma, and do that for every single value that is in x, we're going to get a whole list of numbers z, such that if we plot a histogram, it's going to be normally distributed with mean of 0 and a variance of 1. So you can imagine this z-score as just rescaling this x, just rescaling it so that the mean becomes 0 and the variance becomes 1. Right, so we've just said what the z-score is. So why would we want to rescale the x into z? Well, there are two reasons. One, if we have the z-score for a particular value of x, we know where that score lies compared to the rest of the data. We can make statements like this particular score is above the mean or below the mean. Or we could say things like this 20% of people has scored less than this particular z-score. Or this person who scored this z-score is in the top 1% of all scores. A second use of the z-score is that we can compare scores from different normal distributions. Now in this video we'll just focus on the first reason, which is the score tells us how that score is related to all the other scores. Okay, so using the z-score we can go from x, which has an arbitrary mean mu and a variance sigma square, and it takes us to a random variable z, which is normal, mean 0 and a variance of 1. The process, jargon, process from going x to z, that is called standardization. Right, the Americans use z here, we use an s, let's write it the American way, standardization. And the z, which is a very specific kind of normal because it has a mean of 0 and a variance of 1, we call this the standardized normal distribution. Standardized normal distribution. So when we use the word standardized, it means it's got a mean of 0 and a variance of 1. It's a normal distribution with a mean of 0 and a variance of 1. So note standardization and the standardized normal. To appreciate why we have to standardize, let's consider a problem. So let's the random variable be normally distributed with a mean of 50 and a standard deviation of 10, hence the variance of 10 squared. The question is then, what is the probability that x will be less than 40? Let's try to think of the picture for this problem. Well, x is normal distribution. Oops. It has a mean of 50. Now recall that the area under probability curve comes to 1, right? So this area comes to 1. We want the probability that x is less than 40, so I think you'll agree that 40 is to the left of 50, so let's just say it's around here. To say probability that x is less than 40, well, all these values to the left of 40 is what we want, so the area beneath the curve in that region will be that probability x is less than 40. Now using common sense you can see the answer must be less than 50%, since this normal distribution is symmetrical around the mean, so it's got to be 50 to the left hand side of that, 50% is to the right of the center. Okay, so how do I calculate probability x is less than 40? Well, this is where we can think about stats tables. And here I can hear some of you doing a virtual groan because some of you hate looking at stats tables. It's a very old-fashioned way of solving a problem, but for a first year undergrad or school kid, yep, you'll need to learn tables. So it's at this stage you look at the back of your textbook and look up the normal distribution, isn't it? Well, answer is no, because those normal tables at the back of the book isn't for this specific problem. Okay, now if we had a table, a normal table, that is specifically for a normal with a mean of 50 and a standard deviation of 10, we could look up the table for this problem. But the thing is that the standard tables do not give us, oh, that's junk. I'll just stop the phone there, that's a junk call. Okay, I guess the message there is always disconnect the phone before you start a video. Anyway, where was I? Yeah, look, we want to solve the problem x is less than 40. Now, if we had a table specifically for that the random variable is normal with a mean of 50 and a standard deviation of 10, we can solve that. However, If you think about it, if we have various problems to do with the normal distributions, they don't necessarily have to have a mean of 50 and a standard deviation of 10. You could have a mean of 100 and a standard deviation of 2. You can have a mean or have a problem where it's normal with a mean of 2 and a standard deviation of 0.05. And I think you can imagine many more combinations problems where you can have different means and different variances. If you think about it, there's an infinite combination, isn't there, of values for mean and the variance. So in that case, if we were using tables, we'd have to have infinite many tables to cope with all the possibilities of different values of the mean and variance. And you know that is not possible to have an infinite many number of tables. But there is a way around it, and it's this way: standardization. Because this is now, you're going to appreciate why we standardize. Any problem where x is normally distributed with some mean mu and any variance sigma square, we can recast that problem into in terms of a standard normal, right? And so we only need one table. We only need the table for this standard normal, i.e. a normal with a mean of 0 and a variance of 1. And it's why when you look in the back of a textbook, you will see that the normal distribution given there is not any old normal, it's the normal for a standard distribution. So let's have a look. Okay, this is one taken from our website, my website, statisticsmentor.com. Look carefully. The cumulative standard normal, right? So we know that the standard normal now means that it is a normal with mean of 0 and a variance of 1. Okay, so now that we appreciate why we have to standardize, solution. Let's recast this problem, that probability x is less than 40 in terms of a standard normal. So that will be, we take the left hand side x, we know that we have to, by standardizing, we use the z-score, so subtract the mean divided by the standard deviation. Mu here is 50, standard deviation is 10. Okay, so we do that to the 40. 40 subtract 50, which is the mean for this problem, divide by 10, which is standard deviation, and we have this whole thing by definition is z less than 40 minus 50 over 10. That's minus 1. In terms of a picture, how does this look? Well, it looks like this. Z is z now on the horizontal axis. It's centered around 0, and we want area less than minus 1. Okay, and now we just need to look up in the table, simply look up in the table for this probability value. So this is the area to the left of minus 1. Let's do that now. Okay, as I discussed on my website, in stats tables, you've got to be careful of the normal because there are something like 3 versions of how the tables are presented. What we're looking here is a cumulative standard normal. So cumulative means that I'm looking at this problem probability where z is less than a value a. Right, our value a here is minus 1. Now we note that the z values along the vertical and the horizontal and everything in the body, these represents the cumulative probabilities. Okay, everything which isn't bold. What we can see is that the z values, none of them, they're all positive, none of them are negative, but we want a negative one. That's easy to get around because we can use the idea of symmetry. So we can say that this would be equivalent to, if we just think about a mirror image, using the idea of symmetry, a mirror image, look, if we flip this one, flip it over 180 degrees, still 0. Would you agree that the left and the right will be the same if I do this? Think of it like a jigsaw, they match, don't they? Those areas must match. Okay. So in other words, that z is less than minus 1 is saying that z is greater than plus 1. Alright? Just to be sure, you can see that this area must be less than 50% because it's less than the center of 0. This is greater than the center of 0, it's at 1, so the area here must be less than 50%. Just using our common sense before we look at the tables. So we'll know that looking at the tables, we're after a figure which is less than 50%, i.e. less than 0.5. Okay. Since we are using the cumulative normal gives us area to the left of the curve, left of the point, sorry. So if we're wanting 1 here, we want area in the shaded region, our table is not going to give us that. It's going to give us, let me change color here, it's going to give us this bit here, this area. Okay, so to get the shaded region we want, we're going to find, the table is going to give us this value, which is bigger than 50%, and we do 1 minus this value. Because remember, I said that the area under the curve adds to 1. So think of it like a jigsaw. 1 is equal to this area plus this area. And the table is going to give us this area. So we simply just want 1 minus this area. Okay, back to the tables. So we look, how do you read this table? You look down vertically to get your first 2 numbers, and then horizontally to get the second decimal place. So we want 1 exactly. So go down here, 1.0. All right. And for the second decimal place, we want 0 because it's 1. So that gives us exactly 1. So its area here is 0.841. So we have here 0.8413. So showing my working, make this neat and tidy, we want probability of z is less than minus 1, which we've discussed is the same as the probability that z is bigger than 1. And then we look to this picture here to see that it must be 1 minus probability that z is less than 1. We use the table to look up this probability, which came to 0.8413, 0.8413, and then write down the final answer. That comes to 0.1587. So to answer my original question, what's the probability that x is less than 4? Probability that x is less than 40 is same as the problem of solving that z is less than minus 1. Sorry, I see that. And that comes to 0.1587. So the probability that x is less than 40 is about 0.16, or you could say the 16% chance, however you'd like to see it. So the mechanics we've just done there is to show you that we've finally reached a conclusion where you can say that this score relative to the other scores is like this, or in this case this score, chance of getting less than this score is about 16%. If this was a kind of an score from an exam, then you could make a sentence like about 16% of people scored less than this particular this score 40. Okay, so what we've just done there gives us a very specific answer. Suppose we're not after a very specific answer. Suppose I just know the z-score. Let's just look at something very general, z-score. So if the z-score comes out to be a positive number, that is coming out to 0, or it comes out to be a negative number. Well, if it comes out to be a positive number, think about my picture. Still can't draw. That's around 0. So positive means you're, to the right of this plus sign, it means you've done better than average. So in other words, you've scored above the mean, so you've done pretty well. So score above the mean, because it means that you're down here somewhere on, let's make it very clear, this somewhere along here, yeah? We're not talking about shaded region. Z doesn't denote that, Z denotes a score along here somewhere. If you score exactly, if the Z score for something turns out to be 0, well, that means compared to the others, how have you done? Well, you've done exactly the average, haven't you? Because it's exactly the average, or the mean. You've got a mean score there. How if it's negative? Then what is the score compared to the other scores? It's below the mean, because at 0 and below the mean is somewhere around here, so that score is below average, below the mean. Now, for one more interpretation of the z-score, let's look at it. Let's rearrange it back for x. So say, question is, they could give you in a question the z-score for something and the mean and the standard deviation, and then they could ask you, well, what is the original x value? Could do that. Okay, well, this is an exercise in rearranging an equation. So we bring the sigma up and then take the mu to the other side. So take sigma up first, that gives us this, then add to both sides mu, that gives us, if we take x to that side now, it gives us this key equation, which we're now going to interpret. So it's saying that the original score x is equal to the mean plus the z-score times the standard deviation. Okay, so here it is again, so it can be clear. Now, let's interpret this thing. Say that we have a problem where we find that the z-score is 1. How can we interpret that in terms of the original score? Well, I can say that the score is 1 standard deviation above the mean. Okay, so z is 1. We can say from this equation that the score x is 1 standard deviation above the mean mu. How did I come up with this sentence? Well, look at the equation. This says that x is equal to the sum of 2 bits. It's equal to the mean of x plus some distance away from the mean. I think it's helpful to draw this again. X this time along the horizontal, not z, and this specific bit is mu, obviously. Right, let's do mu is that centered, this whole line is x. What this is saying is that the score x, which is along here somewhere, is that it's equal to mu, right here. Let's circle it to be clear, that is mu, plus some distance away from it. Okay, that length there, say, is z times sigma. Can you see that? So what this says is that z-score is equal to, you start at the mean, mu, and then you add on however far you are from the mean. And however far you are is measured by this, the z-score times the standard deviation. So here, z is 1 means that the score x is 1 times sigma, which is the standard deviation. In other words, 1 standard deviation above. How do I know it's above? Because here is a plus sign. We are to the right of mu, so it's above the mean. So we get the word 1 standard deviation, because this 1 is the value of a z. This is just the sigma. Above, because we have plus sign here. Okay. To be clear, let's consider another example. Let's say that z is minus 1. What's our conclusion now? We can say that the x-score is 1 standard deviation It's no longer a plus sign, it's now a negative sign. So we say below the mean. Hang on, sounds like there's a delivery. Okay, just for practice, here's some z values here, 4 of them. Just make up the sentence like I've done. Just give you a moment to do that, and then we'll just go through them and then we'll end the session. So at this stage, pause the video and just attempt those 4. Okay, you've had a go at that. I'm gonna release the answers after 3. 1, 2, 3. Okay, so quickly, in case you can't read my handwriting, z of 1 means score x is 1 standard deviation above the mean. Z of minus 2, score x is 2 standard deviations below the mean. 1.96, score x is 1.96 standard deviations above the mean. Z equals 0, score x is the same as the mean. Well done if you got that. Okay, well done. So we've looked at one use of this z-score. In the second part of this video, we'll look at how we can use the z-score to compare scores from different normal distributions.